So far, we've covered simple and compound interest, and we also covered the future value of ordinary annuities. Today's lesson is all about the present value of an ordinary annuity, which basically means we want to end up with, for lack of a better way to put it, $0 in the future. So we want to put in some amount of money into an account today so that we can withdraw or pay off some amount of money every month, every day, every week, etc. So present value is today's value of having equally spaced payments sometime in the future. So in this example, Richie Rich wants to invest a sum of money into an account that pays 8% interest compounded annually so that every year for 5 years he can withdraw $500. So we want to figure out how much money he should be putting in today into the account. So this is the present time. So what is the present value of having $500 a year for the next 6 years at 8% interest? So basically he wants to be able to withdraw $500 after year 1. And then also another $500 at the end of year 2, at the end of year 3, at the end of year 4, and at the end of year 5. Okay. Take the compound interest formula, A equals P1 plus I to the power of n, and now we're going to rearrange it to solve for the present value. Since we know what the future value is, we want to know how much he should put into the account today so that 1 year later he will end up with $500. Okay. So we would say a over 1 plus I to the exponent n, or if you like, you can rewrite this as a 1 plus I to the exponent negative n. So let's work backwards for every year. So he needs to put in some amount of money so that after 1 year he has $500. Okay, so he's earned 1 year of interest. He also needs to put in some amount of money today so that 2 years later he will have earned $500. And to get to that $500 he would have earned 2 years of interest. Okay. So continue this pattern for the third year. The exponent on 1.08 will be 3. For the fourth year it will be 1.08 to the exponent 4. And for the fifth year 1.08 to the exponent 5. Okay. If you actually put all of these numbers into your calculator and add them up, then you should get the total amount. So P1 up to P5, when you add them all up, you should get $1,996.36. Now, drawing the time diagram can get really time consuming depending on how many compounding periods you have, how many years we were talking about. So instead, we're going to come up with the formula for this. Now, if you notice, the amounts at the beginning of each year would represent a geometric sequence. And in order to find the total amount for the sum, then we would just use the formula for the sum of the geometric series. So I'm going to write it all out in one line, P1 plus P2 plus P3 plus P4 up to P5. So this is 500 over 1.08 plus 500 over 1.08 squared, 500 over 1.08 cubed, 500 over 1.084, 500 over 1.08 to the power of 5. Now, if you notice, for the geometric series, our first term, A, would be 500 over 1.08. We keep multiplying by 1 over 1.08. That is our common ratio R. Okay. And we have 1, 2, 3, 4, 5 terms in total. So I'm going to use the sum of the geometric series formula. And now I'm going to plug everything in. Okay, this is going to get a little bit confusing. So 500 over 1.08, that's the A value. R is 1 over 1.08 to the power of 5 minus 1 all over 1 over 1.08 minus 1. I'm going to continue this in the next video just to give us a little bit more room to explore how we'll be able to come up with the new formula for the present value from this statement.